Welcome to the lecture number 71. We have been discussing about the force and the torque due to the atmosphere on the satellite. Okay. So, today we will continue with that, and there are forces also due to various other factors. So, magnetic moment already we have considered. Due to solar radiation also the force acts on the satellite, and also it results in the aerodynamic torque. But the analysis for the solar radiation torque is along the same line as we are doing for the aerodynamic moment and the forces. So, I will do a very short discussion on the solar radiation pressure, and rest of the materials will be uploaded, because it follows the same trend as the analysis for the aerodynamic force and the moment. Okay. So, let us continue with what we have been discussing last time. So, what we did last time, that a satellite is going in the orbit, and let us say this is the center of mass of the satellite. It is moving at the velocity of v c r in the orbit. Okay, and then we consider the atmosphere to be static, and that resulted in the relative velocity, which is the atmospheric particles will be moving toward the satellite. Okay. And we considered it in a small area d a, okay, of length v r, and carried out the analysis. Now, as we are aware of that with the rotation of the earth is rotating on its axis from west to east. Okay. So, this is your north, and downside this is the south. In this direction we show it the east. So, this direction it will be taken as east, and here this direction will be taken as the north at any point, and downward in this direction it will be the south, and similarly here this direction will be the west. Okay. So, as the earth is spinning on its axis, so does the atmosphere. Atmosphere, say this is a layer of atmosphere, I am showing it very thick. Okay. This is not that much thick. Okay. So, atmosphere also rotates along with the earth, almost same angular velocity. Okay. So, depending on the inclination of the orbit, okay, this is the orbit inclined with the x y z plane. So, depending on this inclination of the orbit, your what I want to say here, that if you have equatorial orbit, okay, so and satellite is here, okay, satellite velocity is v c r, which we have written v c r or v 0, I do not remember. Maybe for the v 0 we can keep v 0 is the center of mass, because we are choosing the center of mass, and we assume the atmosphere to be static. Now, the atmosphere is also rotating along with the earth. So, with respect to the atmosphere, this velocity of the satellite, this relative velocity of the satellite will be different. Okay. That means, you have to accordingly work out, say atmosphere is rotating along this, suppose capital omega is the angular velocity of the atmosphere, and earth is moving with respect to the inertial frame along this direction, this is v 0. Okay. So, if atmosphere is static, okay, while the earth is moving. So, in that case we get the relative velocity of the atmosphere as v 0. So, v 0 we have written this, we have worked out, this is the relative velocity when atmosphere is static. But if the atmosphere is rotating, so you can see that the atmospheric particle will also be moving along this direction, and on the at the altitude where you are considering, and suppose this is the equatorial orbit. So, in the case of this is your equator, okay, a rough calculation if we do. So, this is your altitude at the, this is the altitude at the orbit you are considering here, okay, and here this is your say v 0, already it is a given. So, what will be the atmospheric velocity? That will be omega cross the r, where r is the radius vector of this point. Okay. So, this becomes v atmosphere. Okay. So, now with respect to the, and atmosphere has the same rotation almost as the earth, okay, it is a rotation rate. So, in that case this is what we are writing. So, what will be the relative angular velocity in that case? v 0 minus capital omega cross r, okay, where this is referring to atmospheric angular velocity. So, you have to subtract. So, we are dealing here with the relative velocity, that is the part you have to remember. Okay, if you take it in any other orbit, just like I have shown here in this place, any different point. So, accordingly you have to calculate how the v will get affected, the three components of v will get affected. Okay, so, that so many transformation, other things we have done. So, that can be calculated. Okay, so, with the atmosphere rotating, the scene is that the relative velocity reduces. So, with the atmosphere rotating, relative velocity reduces for the prograde orbit. Prograde orbit and retrograde orbit, already we have discussed. Retrograde has different the opposite sense of rotation of that of earth, and prograde orbit have the same sense of rotation as that of the earth. Okay. So, satellite in that orbit basically that will be rotating in the same sense. So, with the atmosphere rotating, relative velocity reduces for the prograde orbit and increases for the retrograde orbit. So, for precise calculation, all these things must be taken care of. Okay, so, the next step now will be that we have to work out, perhaps I have not still calculated the torque acting on the satellite. So, that part I will finish today. So, assuming, so now let us assume, so the assumption I make here, now the assumption sphere is rotating along with the earth. So, in that case we are writing this expression, okay, and it has the, it will also have the same expression as we have derived earlier, only thing here the relative velocity will be changing. Okay. So, earlier we have written df equal to rho a times V r times V r dot d a, and we have also taken into account the orientation of the surface by writing h cos alpha, and then we integrated it and we have got the F aerodynamic. So, rho a can be taken outside, V r square can be taken outside, and this can be written as h cos alpha times V r for this part times V r cap. V r we have already taken outside here. So, this is the V r cap, okay. Or either you use E v cap, and for the area you can use E n cap, okay. Either of the notation can be followed. So, for this we are writing here V r cap, V r is taken outside, and from this also one V r is taken outside. So, the scalar quantity comes outside, V r cap dot d a. So, V r cap dot d a, this we can write as d a cos alpha as discussed earlier. So, this is cos alpha times d a. And then what we did, that V r square we have written it this way, h cos alpha times cos alpha d a, and V r is independent of the integration. So, we took it outside, and rho atmosphere is also independent of the integration sign. So, these are the surface integral, and either you can put here, like I can put here double integral to show that this is over the surface, or single. So, I will not carry this, I will just go along with the single one. Unnecessarily this gets complicated. Okay. Okay, so, this stands here for, I will write it as explicitly, this is surface integral. This quantity we have written as A projected, d a cos alpha is the projected area. Okay. So, element of the surface we are considering. So, d a is its area and V r is here in this direction. Okay. So, perpendicular to V r, what will be the projected area d a, okay, where d a we have taken it inside like this. So, A p that comes for this, and then V r cap. Okay. So, this is what we have derived last time. Using this only we can also find out the torque acting on the system. So, the torque, aerodynamic torque, we can write that as m aero, and this will be given by r cross d f aero, where r is the distance from the center of mass to the on this body. We are calculating torque about the center of mass. So, there can be any surface area like this. So, from here to here, this is the radius vector r to that surface area, and from somewhere the relative velocity, this atmospheric particles are coming here in this direction, and we have taken here as n cap or E n cap. Okay, so the same equation is still applicable. So, we can write here as h cos alpha, which we have taken into account. As you know, this is Heaviside function. So, either it will be 0 or 1 depending on the value of alpha. Okay, so, h cos alpha times r cross, and df we have to copy from this place. This is the quantity df. So, rho a times V r V r dot d a. Okay. Rho a can be taken outside. R cross, we can write here as V r square times V r cap times V r cap dot d a. So, rho a times V r square h cos alpha r cross V r cap, and then this part we are writing as cos alpha times d a. V r cap. Okay, so we can write this as rho a times V r square, and this quantity we can write as. Now, look back here into the on the previous page. This is h cos alpha times d a. Okay, this is the quantity we have written as A p. Okay, so, we will define a new quantity, and in terms of that then we can write the equation completely. So, this will express as rho a times V r square times the projected area C p cross V r cap, where C p A p times C p, this quantity we can write as h cos alpha r cos alpha times d a. So, C p basically locates the center of pressure, means where the effective force is this is called the center of pressure, basically where the resultant force is passing through. So, if you look here in this place, C p cross, this is cap, not this one, this is cap. So, we can rearrange it as C p cross rho a V r square A p times V r cap. So, this quantity then becomes C p cross, this is nothing but, if you look here in the previous page, this is F arrow. So, this is the location of the center of pressure and this is the point and this is the force, the resultant force. So, the resultant force at what distance is acting from the center of mass, that locates the center of pressure, and what is the, say the center of pressure may be here, this may be the center of pressure and this is C p, okay. And F arrow, if it is acting here in this direction, this is F arrow. So, this is r cross F, okay. R vector is, or the C p vector is lying here in this direction. So, from here to here. Thus, your M arrow, this can be written as C p cross F arrow, where C p equal to H cos alpha R cos alpha times d A. And another abbreviation that we have used, this is H cos alpha. So, that also I will write here, H cos alpha times cos alpha d A. This quantity we are writing as A p. This is the projected area. Sorry, here this part A is missing. A p times C p. Okay, so, for the simple case we have calculated the how much we have calculated what is the expression for the force and the torque acting on the system. Now, we can take into account if the satellite is rotating, then what will happen. Okay. So, remember that on the previous page, once we have written this, in this case this V r, this includes effect of atmospheric rotation rate, okay, that we have taken into account, okay, because initially we have started with a static model of the atmosphere and then just by a little argument we have extended it to the case where the atmosphere is rotating. Now, we will extend it to the case where the satellite is rotating with angular velocity omega. Now, if the satellite is rotating, that means in this orbit the satellite is there, this is the center of mass and there is certain element here whose area is d A and this satellite is having angular velocity omega, okay, and the body axis also we can fix here. This is the body axis x b, y b and z b, and V o is the velocity of the center of mass. However, we are discussing about the relative velocity between the atmosphere and the satellite. So, in that case V o is, or V o magnitude, this is not equal to the previously we are using here V r, not equal to V r. This you should keep in mind. Now, if the satellite is rotating, so the angular velocity of this will be added to the velocity. So, the v then we can write as, or the relative velocity we can write as v c r minus omega cross r. Also, if we can write here v c r plus omega cross r. It depends on in which direction the atmosphere is moving and then how you are modeling it. So, say the relative velocity we have taken as, this is the, earlier we have written this as, let us say this is the v c r, means the relative velocity, this is the v c r, relative velocity of the atmospheric particles with respect to the center of mass of the satellite. So, it is including, this includes atmospheric rotation also. Okay. So, if this is v c r here in this direction as we are showing here, and this area it moves here in this direction. So, you can see that there will be reduction in relative velocity. So, in that case we can write as v minus omega cross r. On the other hand, if it is moving here in this direction, so this will be just written as omega cross r, but irrespective of that whether you write here plus or minus, it does not matter. Okay. Ultimately, if you put the proper sign, so you will get the proper result. And one thing you should remember, that if you are writing this v c r as the center of mass of the satellite is moving here in this direction. So, atmospheric particle you are showing along this direction. Okay. So, it is moving along this direction v c r for the atmospheric particles. Okay. So, drag is along this direction. Okay. This is the velocity of the center of mass with respect to the atmosphere. So, drag will be along v c r direction, and it is a way of modeling. In few places you will find this quantity written with minus sign, like the f arrow we have deducted here. If you write with a minus sign here in this place, suppose I put a minus sign. So, this minus sign will refer that you are showing v c r here in this direction, which is in this case not, velocity is not that of the particle, but rather of the satellite center of mass. So, that I have not done here. Okay. So, I have assumed that v c r is the relative velocity of the particles with respect to the satellite. So, they are coming and impinging on the satellite. So, and therefore, this minus sign we are not using here. Okay. So, with this expression we can work out the torque and the force acting on the system while the satellite is rotating. So, now the force acting on the satellite when the satellite is also spinning. So, in that case we can write here then the F aerodynamic force, it can be written as h cos alpha, the same way we have written here rho A times VR times VR dot dA. This is the basic equation we are using. Okay, it remains unchanged. However, here in this case we have to insert the expression for VR. So, VR here in this case this becomes VCR minus omega cross R and then VCR minus omega cross R dot dA. This omega, one more thing I would like to point out here, omega does not include the atmospheric rotation. Which we have included in VCR itself. So, atmospheric rotation has been taken care in VCR itself. So, we do not have to think about that separately. Here we are just dealing with the angular velocity of the satellite. So, this part we expand here VCR dot dA minus omega cross R dot dA. It is cos alpha, rho A we can take it outside and then expand this. So, this is VCR times VCR dot dA minus VCR times R dot dA and then this part minus omega cross R times VCR dot dA and plus omega cross R times omega cross R dot dA. So, this quantity is quite small, this is negligible, this is a second order term, hence neglected. Okay. So, we are left with these three terms which we can work out now. Okay. So, at the next level we have h cos alpha and then VCR square, we can write this term separately and VCR, this particular term we can write as VCR cap. This VCR we are already taken into account here in this place dot dA and times VCR cap. This is the unit vector VCR. VCR is the unit vector which we are defining as this minus then the quantity here. So, this is VCR so rho A times h cos alpha which is here in this place is multiplying to all the terms. So, this then becomes V C R omega cross r dot d a minus rho a times h cos alpha omega cross r times V C R dot d a So, these are the three integrals which we need to evaluate. So, now we evaluate the first integral. V C R square, this is a constant. So, it can be taken outside, and the first term then we can write as. So, therefore, f a rho, this becomes rho a times V C R square and in the bracket h cos alpha, and then we have this quantity which we will write as d a cos alpha. V C R is a unit vector. So, this we can write as d a cos alpha, okay, and then V C R cap. So, V C R cap, this is the unit vector along the center of mass velocity. Okay. Therefore, it can be taken outside the integration sign, and this quantity already we know what this quantity is, but let us write all the terms. Then rho a, this quantity, again this V C R is there. So, we can take it outside. Okay. So, this becomes rho a times V C R, then h cos alpha, and for this we will introduce the unit vector. So, we will write this as the V C R cap, okay, and thereafter the rest of the terms we have. So, this is omega cross r dot d a. Similarly, for the lower one, we can write this as minus rho a times V C R h cos alpha which omega cross r and times V C R cap dot d a. Times V C R cap dot d a. So, rho a times V C R square, and this quantity already we have discussed about this. This quantity is nothing but the projected area. So, A projected area times V C R cap, this is the first term we are having in this place. Then the other one rho a times V C R, this we need to little bit rearrange in a particular way, so that we get a nice solution. We can write this quantity as r cross d a dot omega. Okay. This is the triple dot product. So, we can use this property. So, omega we can separate out, and this can be written as r cross d a dot omega. The third term this quantity we can expand as V C R, there is a unit vector, therefore, we can write as cos alpha times d a. So, few more steps are required to finally get this solution. Now, this quantity again can be rearranged in a particular way. R cross d a, V C R is not dependent on the integration. So, we can take it outside. And if you remember, this is the dot product here omega omega. So, this omega also we can push here on this side. Or either on the right hand side also we can keep it, it does not matter. So, let us keep it on the right hand side. So, this is V r cos alpha r d a times V C r cap. Okay. This dot product is over only this part. Remember, we have to be very particular about on which the dot product and the cross product are operating, and it depends on the way we have written the equation here. Okay. This is very important. So, this bracket must be maintained. If we mix it up, so all the results will be wrong. So, this V C R, because it is a this dot product is with this and this. So, we can write here dot omega, and V C R we can keep it outside, and this term then rho a V C R h cos alpha. We can change the sequence here and write this as with a plus sign, and here we can write as r cross and cos alpha d a. d a is not a vector here, we have already changed that, and outside we can write this as omega. So, this is the way this is working. Now, the quantity we are having here R A cross d a. So, this we are going to define as h cos alpha r cross d a. So, this we are going to write as A p times C p, A p times C a. So, if we do that, so this particular equation then reduces to a format then this becomes A p is a scalar, this is a scalar A p times C a. This is not the center of pressure as we have defined earlier, this is C a, okay. A p times C a, and then if you look into this part dot omega. So, this is dot omega. So, these are together and then V c r cap and plus then we have the quantity which is given here. R cross d a, and this will operate on d a is a scalar here on omega. Okay, so, now we can wind up the thing. So, we can write here F a rho, this becomes rho a V c r times a square A p times V r cap or V c r cap we are writing. So, this is V c r cap and then the second term we pick up minus rho a V c r times A p and this we can write as C tilde transpose times omega times V c r cap, and the other term we have here plus with plus sign. So, that gives us plus here also rho a times V c r and the term which is present here cos alpha r cross d a. So, see the difference between this term here, this is r cross d a and here this is r cross and d a, this is a scalar. So, this cross is working on this omega, not on d a. Okay, d a as well we can write here on this side. So, what it implies that we can write this term as rho a V c r h cos alpha and then cos alpha d a r cross and this is working on omega. So, this is the operation we have to do. Okay. So, while we have written it like this omega, this cross, the cross term is there. So, this cross term is not dependent on the integral sign. So, it will be convenient if we fetch it on the outside the bracket, and then if you look here in this term. So, this becomes A p times C p, projected area times the center of pressure distance. So, using this, then we can write as rho a V c r, then H cos alpha, we write it this way, H cos alpha d a r cos alpha d a times r, and put it in bracket and then put cross here, cross omega. So, the equation gets pretty simplified and comes in an elegant format. Rho a V c r, this quantity is A p times C p and then cross omega. Okay, so, rho a V c r times A p can be taken outside the bracket, and what we get here is V c r minus rho a V c r A p will go from this side. So, C tilde transpose A times omega tilde, okay, and then V c r cap this also goes outside, and we get here C p tilde cross omega. So, this is the aerodynamic torque acting on the system, force acting on the system if the satellite is also spinning. So, we will continue in the next lecture. Thank you very much for listening.